Hello everyone, how's it going? My name is Dan the Tutor. Today we're going to be talking about exponential functions. So let's start off with an example of when we would use exponential functions. So let's say you start with a population of flies that starts with 100 flies in this ecosystem. And then let's say every day the number of flies doubles. So after day 1, you have 100 flies. After day 2, you're going to have 200. After day 3, it doubles again, so 400. And you can imagine this is going to get pretty big pretty quickly. 1600, 3200, eventually 6400. It eventually goes up every time. But notice here the trend is that every time you are multiplying the number of flies by 2. This is what makes it an exponential function, when we're multiplying by some number every time. Now let's talk about the equation that can be used to model this scenario. The equation for any exponential function is y equals a times b to the x power. Another way you can write this is a and then in parentheses b to the x, but that's the exact same thing, it's just multiplication. And what you should know is that a, variable a, is your initial amount, how much you're starting with. And then b is going to be our multiplying factor. So in the last example, the multiplying factor would have been 2 because we were doubling each day. As a matter of fact, if we want to model the last equation, we started with 100, so that's a, and then times b, which again I said was 2 to the x power. Now the biggest mistake you can make here is you can multiply the 100 and 2 together to make 200. I repeat, this is the biggest mistake you can make. Never do that. You cannot combine the 100 and the 2 to the x because of the fact that these are not like terms. This is to the power of x. So please don't do that. That would be horribly wrong. And let's say instead you wanted it to triple every day. Well, then you would just write y equals 100 times 3 to the x power. Or if you wanted to start with 1,000 flies instead, you just add a 0 to the initial amount. So there's a lot of flexibility with what you want to do here. As a matter of fact, you can even make it go down each time. Let's say the number of flies goes down by 1/2 every day. So 100 times 1/2 to the x power. So as you can imagine, there's a lot we can do here with exponential functions. We can have numbers increase exponentially, or we can have them decrease exponentially. Now let's talk about the graph of the exponential function. So first of all, there's 2 points you should always know that will always be on the graph for x and for y. The point 0, a and the point 1, a times b. And the reason why this makes sense is because if I have the function y equals a times b to the x, and you plug in 0 for x, well that's y equals a times b to the 0. Anything to the 0 power is just 1. So that becomes y equals a times 1, which is just a. So that's why when you plug in 0, you just get a. And remember, a is your initial amount, so whatever that is. In the last example, it was 100. And then when I plug in 1, I would get y equals a times b to the first, which is the same thing as just a times b. And those are the 2 easiest points to find on an exponential function. And so, for instance, that means if I wanted to graph the last scenario, and by the way, the exponential function will always look like this. Well, actually, that's a lie. This is if it's exponential growth. It looks slightly different if it's exponential decay, and I'll show you what that looks like too. But I know for sure I have 2 points. In the example y equals 100 times 2 to the x, I know I have the point 0, 100 because that's my a, and then I have the point over here 1, 200. And why 200? Because a times b is 100 times 2, so 200. So I know I have these 2 points. And then if it looks like exponential decay, it basically looks like the same thing, except the graph would start high and then go down low like that. One thing to note with the exponential function, this is true for both exponential growth and decay, is that there is a horizontal asymptote at y equals 0. In other words, you're never going to cross to the negative axis. Now what's cool is, if I wanted to, I could actually find the equation if I give you the curve In other words, let's say I have this exponential growth curve right here, and I give you the points 0, 20 and the point 1, 30. Well, you can easily find the equation because A is just the starting amount, A is 20, and if you want to find B, well then you use this point right here. You would say first y equals 20 times b to the x, and then you plug in 1 for x and 30 for y. So 30 equals 20 times b is what we're solving for, and that's raised to the first power. So that means 30 equals 20 times b, divide both sides by 20, and we'll get b equals 1.5 or 3/2, depending if you like fractions or decimals. And there you go, the final equation of that graph that I didn't know a second ago is now 20 times 1.5 to the x power. And that's how we can find graphs of these exponential functions. And then the last thing I want to talk about today, this is probably the most important part, and when exponential functions are used the most, is with percentages. So the equation changes just slightly for percentages. Let me show you. Instead of y equals a times b to the x, I'm going to write y equals a parenthesis 1 plus or minus the percentage raised to the x power. Now let me show you an example of this. Let's say the price of a home increases by 10% each year. And what I want to know is how much will the home be worth after 5 years if you bought it for $400,000. So this is a real world example actually. Houses don't go up by 10% each year, but 10's a round number. It's going to help us out with the math. But the price of your home will increase by some percentage each year, and you can actually calculate the value of your home using these exponential functions. So as I said, y equals a times 1 plus or minus percent to the x power. The percentage here is 10%, but you don't write 10% there. You need to convert that to a decimal, which you can do by dividing by 100. 10 divided by 100 is 0.1. So that means the equation becomes y equals the starting amount, which was 400,000, times 1. And then for the plus or minus, it's plus when it's growth and minus when it's decay. Since our home is going up, we do want the plus, so it's 1 plus 0.1. And the x power is how many years? In this case, 5 years. And so if you want to calculate the price of your home, you just have to plug this in your calculator, which I will do now. And I will get y equals $644,204. And there you go. That's how you can use percentages as well with these exponential functions. And again, if for some reason the price of a home went down by 10% each year, it would have been the exact same equation, except it would have been 1 minus 0.1 to the 5th power. And there you go. That's everything you need to know for exponential functions, at least as a basic introduction. So thank you all for watching. I hope you have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.